In Chapter 1, we talked about different ways to combine functions into new functions. We could add, subtract, multiply, and divide them, and we have rules about how to differentiate functions when we do that. But we also had one more important combination called composition. Basically the idea of putting one function inside of another function to get a brand new function. So something like, let's say f of x is equal to the square root, not just of x, but of 3 minus x squared, where we have an inside function, this 3 minus x squared, and an outside function that is the square root function. What we want to do today is figure out how to differentiate such a function, at least without having to go back to our limit definition. And that rule for doing so will be called the chain rule. So let's first set this up. Let's say we have a composition, so something like g of f of x. Now this is a new function. We could give it a new name if we wanted to. We could call it h of x. But the idea here is that we start with x's, and f will change an x into something else. Let's call it a u just to kind of help us out here. Then g sees whatever f got from plugging in x, this u, and it changes that one into a y, into the y value. So instead of having, say, h of x here, maybe we're just saying y equals. So we get from x to y eventually, but we take this detour through u. Essentially here we're saying that u is equal to f of x, and that y is equal to g of u, which is the same thing as g of f of x, because we're just plugging in that value for u. It turns out when you look at these compositions and you want to take our derivative, it turns into a product. So the chain rule has a couple different forms. First things, if we want to differentiate this y value, the composition itself, with respect to the original variable x, then it's the same thing as if we took the derivative of y with respect to u first, and then took the derivative with respect of u with respect to x, and multiply those two results together. Another way of writing this, and this is the one that's going to be actually a little bit more useful to us, if we want to differentiate g of f of x, it's the same thing as the derivative g of u times the derivative of f of x. So g here, even when we take the derivative, we do not just plug in x. We can't just plug in x to it. What we end up plugging in is the u. But the u is just f of x. So we are going to basically take the derivatives of both our outside and our inside function and multiply them together, but remember that the derivative of the outside function still has to have the original inside function inside of it. Now, if we do want to prove this, there are a few technicalities that I'm going to just kind of ignore here. This is not a formal proof, but it will give a basic idea of why it turns out that we have this formula. So remember that we have u equals f of x, so that we're differentiating g of u essentially. I'm going to call, not du, delta u. I'm going to call delta u f of x plus delta x minus f of x. And that means that because f of x is just u, if I add this u to the other side, I have u plus delta u is equal to f of x plus delta x. Essentially, if I'm going to make a small change in my x value, it will result in a small change in my u value. So when I set up my derivative for g of f of x, This is the limit. So we're going back to our limit definition here. As delta x goes to 0 of our function at x plus delta x minus just the function itself. Of course, the function in both these cases is g of f of whatever we're putting in it. Then we divide that by delta x. And so the idea here is that because I've defined this delta u in this way, I can replace the f of x plus delta x with u plus delta u. Well, I'll have to do that on another page. Kind of ran out of space here. So we're going to have g of u plus delta u minus g of, well, we had g of f of x. Of course, f of x is u, so I'm going to go ahead and replace that with a u. And I forgot my limit. Don't forget the limit. So this is the limit as delta x goes to 0. I still have a delta x on the bottom. And notice here that what we have on top is what we'd expect to have in the formula for the derivative of g. The problem here is that on the bottom we have delta x. We don't have delta u like we'd have to have for the derivative of g. We also don't have the correct limit over here. We need delta u goes to 0. So we're going to have to fix those problems. We're basically going to have to change our x's here into a u instead. Or, well, the delta x into delta u. Now what I'm going to do is actually, I'm going to multiply the top and bottom of this fraction by a delta u. So I'll still have this stuff on top. I'm going to actually move this delta x over to its own fraction over here. And then I'll multiply the top by a delta u and the bottom by a delta u. The idea here is that now this fraction is exactly what we want to have for the derivative of g. But we have to figure out what this fraction is. But remember what delta u is. Delta u is the difference f of x plus delta x minus f of x. That's what we called it. So we'll still have this first fraction. But then this fraction, it'll still have a delta x on the bottom, but the top is now going to be f of x plus delta x minus f of x, because that's what delta u actually is. And so now what do we have? Well, we have these two fractions, both of which are exactly what you'd want to have for the derivatives of f and g. In fact, as delta x goes to 0, this one over here turns immediately into the derivative of f. This one over here, we have to think about it just a little bit. But keep in mind, as delta x goes to 0, if we go back to delta u, if delta x is going to 0, then this part is going to f of x, because f is a continuous function. We're assuming here that f has a derivative, so it's continuous, and so this first part is definitely going to f of x. So we'll have an f of x here, we'll subtract an f of x on the end of it, and so the delta u is actually going to 0 as well. And so even though we don't have a limit as delta u goes to 0, this is really forcing delta u to go to 0 anyways. And so this first fraction is going to go to the derivative of g. Now technically that's of u. So we have the u's in here. So this is derivative of g with respect to u. But that's the same thing as the derivative g of f of x, because that's what u is, times the derivative f that we have over here. So essentially we had a fraction involving g's of f of x when we managed to split that up into two different fractions that were multiplied together. One for g and one for f. And so that's the basic idea here, without some of the technicalities that technically we'd have to worry about if we were wanting to do this more formally. But that's not really the point of this class. It's definitely not a proof-based class. In fact, I wouldn't go over this in a regular Calc 1 as well. That's more the realm of say, advanced calculus. Let's move on to some examples, though. Let's work on problem 7. In problem 7, we have y is equal to 4x plus 7 squared. And we want to use the chain rule to differentiate this function. Now, they didn't give a name to the function. We could call this f of x if we wanted to, but that's not really the point. The point is here that we have y is equal to some function that is comprised of two different functions. We have an inside function, which we'll go ahead and list out here. The inside function is the 4x plus 7. The outside function is the square. We can say that y is equal to u squared. What we're going to do is take the derivative of both of these. The derivative of u with respect to x. Of course, here that's just going to be a 4. In fact, maybe we should, instead of just saying u prime, if we want to specify here what derivative we're actually working with, this is du dx. Because the function that we're differentiating is u, and the variable that we're differentiating over is the x. Over here, if we differentiate y with respect to u, well, the square function when we differentiate it is just 2u. Or it would be 2x if we were working with x's here. So the derivative of y with respect to x, not with respect to u, not this derivative over here, the derivative with respect to x is going to be the product of these. We're going to have the 2u times the 4. Or in other words, we have a 8u. But of course, we don't want it in terms of u. We didn't even have u's in the original problem. We need to replace this u with the formula in terms of x. So this is 8 times 4x plus 7. Or in other words, we have a 32x plus 56. And that is the derivative of this function. Now, of course, in this particular problem, we were not really required to use the chain rule to get our answer. This is just a square of a binomial. We could expand it out. And let's do that in order to compare to what we got using the chain rule. So the alternate way of doing this problem would be to just FOIL this thing out. If we FOIL it, the 4x in the front is going to be multiplied by another 4x, so we'll have a 16x squared. We'll have a 4x times 7, or 28x, but we'll have 2 copies of that. So we'll have should probably multiply by 2, 56x. And then finally we'll have 7 times a 7 to give us a 49 at the end. So this is the same functions that we have up here. If we differentiate this function, well, we take this x squared and differentiate it, get a 2x. That 2x times the 16 that we have there is going to give us a 32x. Here we have 56 times 1, because the x will become a 1. So we just have a 56. And of course, the plus 49 is going to go away because the derivative of a constant is 0. And so we get exactly the same answer as we got up here. Now, you might look at this and say, well, this seems a little easier. Well, that's because of the particular function that we have. Not every function can be done by expanding out. In fact, if we move on to problem 9, this time we have y equals the square root of 3 minus x squared. Of course, this is the one that we looked at the very beginning. I said that we needed some other rule to be able to deal with this. Without the chain rule, we can't really differentiate this function. We can't skip that chain rule by expanding something this time. So we need to actually split this up into an inside and outside function. The inside function here, which I'll go ahead and call u for the moment, is going to be 3 minus x squared. The outside function is y equals the square root of u. Of course, to differentiate this, we want to interpret the square root as a fractional power. This is really u to the 1/2 power. And now we go ahead and differentiate both of these. The derivative of u with respect to x, well, the 3 goes away, and we have a minus times the derivative of x squared, which is a 2x. The derivative of y with respect to u, again, we're going to use our power rule here. We have to think about it a little bit more because we're not as familiar with it as x squared. But we take that 1/2 power, we bring it out in front, and then we reduce the power by 1. 1/2 minus 1 is a negative 1/2. Now I'm going to actually go ahead and interpret this back as a square root. Remember, the negative here means that we are working on the bottom, and the 1/2, it means that we're dealing with the square root. So really, we saw that 2 on the bottom, but now we also have a square root of u on the bottom. And so our chain rule tells us that to find the overall derivative, the derivative of y with respect to the x and not with respect to the u, is we take the product of these two things. We have the 1 over 2 square root u times the negative 2x. And there's a couple things I want to do here. First of all, might as well cancel out those 2's. I'm going to go ahead and move the negative x up on top. And then we have a square root of u on the bottom, but we want to make sure that all the u's are back into x's. So we'll have a square root of 3 minus x squared, because that's what u actually was. And that is the derivative of this function, without having to do anything with limits. Let's move on to problem 12. This time we have y is equal to x cubed plus 2x squared to the negative 1 power. Again, we have an inside function. The inside function here just being the x cubed plus 2x squared. The outside function being u to the negative 1 power. If we take the derivative of the outside function and multiply it by the derivative of the inside function, I'm not even going to write out the derivatives of these two functions separately now. Let's just work them out as we go. The derivative of u to the minus 1 power, remember that is a power of x, or well, a power of u here. So we'll have a negative, that negative 1 gets pulled out in front. Then we have u to 1 less power, so negative 1 minus 1 is a negative 2. That's the derivative of the outside function. If we multiply by the derivative of the inside function, this x cubed plus 2x squared, x cubed becomes a 3x squared. Remember, we brought down the 3, and then we reduced the 3 down to a 2. And then 2x squared, well, the x squared becomes a 2x, times the 2 that's already there, and we get a 4x. And finally, since we don't want to have the u in there anymore, we want everything back in terms of x, just replace it with what we have for u. So u is x cubed plus 2x squared. Everything else is the same. And that's our derivative. But there's actually something else that I want to say about this in this particular problem. Let's think about what these negative exponents really mean. The negative 1 power means that what we have inside of here is on the bottom of a fraction. Basically, our original function here is really 1 over x cubed plus 2x squared. And the derivative that we got, this negative 2 power here, means that this is on the bottom and squared. Our derivative is really, we'll go ahead and keep that minus sign out in front. We have an x cubed plus 2x squared on the bottom. And then I'm going to go ahead and put this on top. 3x squared plus 4x. This function was a fraction, or we could say a quotient. We could have used the quotient rule here instead of using the chain rule. And the derivative that we got here is kind of reminiscent of what the quotient rule already tells us. Notice here that what we had on the bottom originally is still on the bottom, but it's now squared. And we can kind of see that the squaring that we got in the quotient rule actually comes from something that you could see in the chain rule. This -1 power becoming a -2 when we use the power rule is the same as our bottom becoming squared when we use the quotient rule. Essentially what this is showing us is that we can get the quotient rule by combining the product rule with the chain rule. And let's go ahead and let's actually do that. There's a reason why I didn't want to prove the quotient rule directly from the limit definition, because once we have the product rule and the chain rule, we can get the quotient rule a lot easier than going through all of that algebra. So I'm going to differentiate f over g. I'll leave off the of x part, because I don't really need it here. We can treat this as the derivative of f times g to the -1 power. Because that's what a g on the bottom is. It's really that whatever's on the bottom to the -1 power. When I use the product rule on this, because this is now a product of the function f and the product g to the -1 power, I take the derivative of the first part, the first factor here, times the second factor as it already is. So let's just leave that as a g to the -1. Then I'll leave the first factor alone, just f as it already is, times the derivative of the second factor. I'm not going to differentiate that quite yet. I'm going to leave it as just the derivative of g to the -1. But how do we take that derivative? Well, this is really a composition. The inside is the function g. The outside, you could say, is u to the -1. Just kind of exactly what we were doing back here. We had u to the -1, and we had a function inside of it. Of course, in this particular problem, we didn't have anything on top. It was just a 1. Here we have all these f's just because we want the more general rule. So when we go ahead and actually use the chain rule, well, we still have all this other stuff. We're going to take the derivative of u to the -1. Remember, that means that we have a negative, say u to the -2. I'm not going to write the u in there. I'm just going to write it as the g that we already have inside of it. So you have a negative g to the -2. But then we also have to multiply by the derivative of the inside function. So this is the derivative of the outside times the derivative of the inside. Of course, I don't really want to have these negative exponents if I can help it. And I'm also going to move that minus sign to the middle. So this is going to be f prime over g. This one's going to be minus the g to the -2 means we have a g squared on the bottom. And on top, we still have this f, and we still have the g prime. Okay? And really, we could actually take that as our quotient rule if we wanted to, but normally we go ahead and just combine the two fractions. So here, what we're missing, well, we have a g and a g squared. We want to have a g squared here, so we're going to multiply the top and bottom of this by g. And that means on top, we now have f prime g, this part here, minus fg prime. And the bottom is all g squareds. And that's exactly what we had for the quotient rule. This is exactly what we had in that case. And you can kind of notice where some of these parts of the quotient rule came from. The fact that we have the square on bottom and the fact that we have a minus sign here both came from the fact that the derivative of 1 over x is 1 over x, well, negative 1 over x squared. Essentially, the stuff on the bottom, the fact that we had stuff on the bottom, we square that stuff on the bottom and we introduce a minus sign. At least when we're taking the derivative of the stuff on the bottom. So that's why I always like to keep in mind which of those terms has the minus sign corresponds to wherever differentiating the stuff on the bottom. It all boils down to exactly this fact. Let's go ahead and actually see this in action. Let's look at problem 13. Here we have a function f of x is equal to 2 over 1 minus x cubed. The fact is that we could either use the quotient rule or the chain rule to differentiate this function. Just because the chain rule is the newest one, I'm going to go ahead and keep using that. That is what this video is specifically about. So I'm going to interpret this as a chain rule problem. But you probably want to actually try it out and see that what we get from this problem using the quotient rule is the same thing. In order to do that, I'm going to reinterpret the stuff on the bottom as a negative 1 power. So I'm going to have 2 times the 1 minus x cubed to the negative 1. When I differentiate this, I'll still have the 2, but I need to differentiate the outside function. The outside function here being the negative 1 power. Of course, we're going to have to use the chain rule, use the power rule there. We bring down that negative 1, and we change the power. We subtract 1 from the negative 1 to get a negative 2. And we need to multiply by the derivative of the inside function. Derivative of 1 minus x cubed. The 1 goes away, but the x cubed becomes a negative, negative x cubed becomes a negative 3x squared. And in fact, we can go ahead and now put this back as a fraction. This negative 3x squared goes on the top, actually along with the negative 2, and this is now a square on the bottom. So we have a 1 minus x cubed squared on the bottom. We have 2 negatives that actually cancel each other out. 2 times 3 gives us a 6, and we still have an x squared. Alright, once again, I'm going to go ahead and split this video up into 2 parts, just to kind of give you a little bit of a break between all these examples that we've been doing here and some more examples that we're going to do in the next video. I mean, it's all basically just using the chain rule, though we do have a couple other little side topics to talk about. But I'll meet you in that video as well.